Hello again. This time I'm going to present my work, which is a passive sensors for food quality monitoring and anti-counterfeiting. So this is the agenda for the presentation. I'll start with the motivation, of course, and I'll show two sets of work, which is the first steps into the development of sensors using cork. The first is an RFID passive tag design, no sensing capabilities, but designed for be very, very small and conformal to be adapted to bottle stoppers. And then on a second set, I'll show the design of a passive humidity sensor based on RFID using the cork properties. So motivation, I think we talked a lot about RFID here today, so of course now most of you already know the advantages of RFID and all sorts of places where it's being used, and it's a growing technology. It's being applied to a lot of different applications and scenarios, and therefore it's a very interesting thing to invest on in terms of research. Of course, it's a major enabler of the Internet of Things, or Internet of Everything. But the real motivation for part of this work, the spiritual beverages market is a potential target application of this technology. They are very conservative about the application of technology in their products, but still they are open to, especially the high cost brands. They are open to introduce new products and new technology into their products, not only for quality assessment, but also for marketing purposes. So, the introduction of RFID technology in these higher cost brands on spiritual beverages makes easier the process of inventory and tracking of the bottles, allows the control of the quality of the beverages, and it's one way to avoid counterfeiting and adulteration of the drinks. So an RFID tag for a bottle stopper. In order to make it small and conformal, usually the RFID tags are comprised of a matching network. Usually it's an inductive loop, plus the antenna, the dipole arms, which can take many forms, many adaptations to make it adaptable to the scenario they're going to use it. But in this case, what we decided to do is to get rid of the dipole, get rid of the antenna arms, and pick up the inductive loop. So by controlling the dimensions of the inductive loop, and we know that we can reach an input impedance seen from that point, the red triangle. We can manipulate the inductive loop, and considering there's capacitance, parasitic capacitance forming inside the inductive loop, in order to reach an input impedance, which is at resonance, purely inductive. So it matches the capacitance characteristic of the RFID chip. But then we have one problem. The input impedance of the RFID chip as a real impedance, as a capacitance input impedance, but with a real R that needs to be matched, and we are not able to do with just this. So as we don't want to increase the size because we needed to make it really small to fit on the cork stoppers, what we do is we find the point of lowest current density, which is this point on the top of the arms, which is going to allow us to easily match the input impedance of the ring with an SMD resistors. Yes, of course, we lose radiation. We lose the radiation efficiency because it's going to be lost in the resistance. Still, if you look at the final efficiency of the antenna, the total efficiency of the antenna, without the resistance, it's mismatched to the chip, so we get 6% total efficiency. With the resistance, we get 5%. But this is where we have the trick. Of course, these values are for the final design of the antenna inserted into a bottle filled with liquid, which is one of the major problems, which is one of the major contributors to this shift down in efficiency. But so here's the proposed antenna design. It's a looped ring antenna with a lump component matching. And you can see the prototype on your right. This is placed on the surface of the cork stopper, and this is one of the things we're trying to improve now, because for implementation purposes, they don't want anything on the surface of the cork stopper. So we are shifting this to another position. This was the first proposal, the first prototype. This is the RFID we used. So as you can see, the input matching, it's dependent on the material surrounding the antenna, of course. So if we have the standalone cork with the antenna, we have one impedance. As soon as we insert the glass neck around it, we change. As soon as we insert the full bottle, it changes. As soon as we consider the liquid, it changes. So for simulation purposes and to make this work in reality, we have to take into account all the materials used in the application scenario for this antenna, and the presence of the liquids as a toll on the efficiency of the antenna, because if we consider an empty bottle, we get about 40% or 35% efficiency, but as soon as we consider some liquids inside, the efficiency drops to the 5% I've shown you. So the maximum range obtained with the best positioning conditions was 35 centimeters. This is low for a passive tag, of course, but still for the application scenarios, this is supposed to be used. It's still a decent value. Although we were trying to, of course, make it better on this, we're trying to get to at least 1 meter, which is very reasonable for this kind of application, even with the liquids. So on another set, which is still targeted for the food industry, we're designing a passive humidity sensor using the cork properties. So the dielectric properties of the cork in regular relative humidity conditions, which is 40-50% humidity, which is what we usually have inside our houses, labs. It was obtained before, with which the previous models were simulated. And we can show, I've tested 2 different kinds of cork. This is natural cork, and this is pressed cork, which is made with the pieces that are the rest from the processing of cork stoppers. And this is the values obtained for the permittivity and losses of the cork in this not dry but 50% relative humidity. So you can see that the natural cork, it's anisotropic, so it's a different permittivity in both axes, while the agglomerate cork is, of course, isotropic, and also natural cork presents higher losses. But the good thing about the cork is it is porous, so it might be used for air humidity measurements. But why cork? Why use cork and not any other kind of material? Well, the cork is extracted from the cork tree, for those of you who are not familiar with it. But it has several interesting characteristics. It's lightweight. It's very lightweight material. Has a large durability. That's why it's used in wine bottles to store them for hundreds of years. Has good thermal properties. It doesn't conduct heat, so it's very good. And it's rather cheap. We have lots of it. So that's why we want to make the most of this material. So due to the cork porosity, it is sensitive to the air moisture and can be used as an humidity sensor. The permittivity variation of the cork with the humidity we studied with 2 different approaches to confirm the results. One of the approaches designed an antenna in a very thin substrate and place it inside 2 cork slabs and change the moisture, the water content around the cork. And then we got back to the simulator when we changed the permittivity of the cork until we obtained the same resonant values, and we matched the wet cork to 2.6 of permittivity, and the dry cork, of course, around 1.7, 1.6, depending on this 1.7. It's for about 55 relative humidity values, which was the lab content at that time. The other approach was using the same 2-line method that was used before, in a dry and wet condition, and we can see the more or less the same shift between 1.5, 1.55 permittivity to almost 3 or 2.8 in this case permittivity between the wet and the dry conditions, and also an increase in the losses for the wet cork. I must say that this is for the agglomerate cork, not the natural one. So the passive RFID tag is a simple approach. We didn't want to make it. This was the first design. We wanted to make it quick to test the properties. So it's a simple dipole with a matching loop ring on an epoxy surface, which is printed using inkjet printing technology, and it is inserted inside 2 cork slabs. So we can see on the top, on the side view, which is B, you can see the antenna. It's a really thin slice in the middle of the blue dielectric. So considerable threshold power, like minimum threshold power, is obtained between the dry and wet conditions. This is the measurement setup, the first one, and this is the minimum threshold power measurements between the dry, wet, and after 30 minutes of drying, we can see that the response tends to the first approach. This is just preliminary measurements. We now have to perform this under a controlled humidity condition to map these threshold powers to certain relative humidity values, because we haven't done this so far, but that's one of the next steps. So it is shown that it's possible to miniaturize tags to the point of inclusion inside harsh propagation environments such as liquid-filled bottles with careful design. Also, that cork is a very resourceful material and can be used to sense humidity. As a future work, of course, a different tag antenna designed to increase the sensitivity of the dielectric property changes in the cork humidity sensor, and also to verify the results in a humidity-controlled environment. And I finished my presentation. Thank you very much.